Hello everyone, a very good evening to all. Is my voice is my voice clear?
Yes, it's clear.
Okay, so also my screen is visible.
Yes.
Okay, so uh, there might be some noise of dogs, but since I'm out of my lab, so I can't avoid this. Let's hope they stop there. Okay, so once again I welcome you all for this fourth introduction session on atomic and molecular physics, which is being flowed by NPTEL this January 2025 session with course code NPC 25PH04. I am Vivekananda Naik. I am a PhD scholar in the Department of Energy Science and Engineering, IIT Delhi. So we will start our discussions. So today we will solve a few problems that will be covering the course content of the week 4 lectures. Basically, in week 4, we discuss the course lectures were mainly based on the continuation of Bohr Sommerfeld theories. Then there are discussions regarding the advantages and disadvantages of Sommerfeld's modification to the Bohr's theory. Then we come towards different quantum numbers like spin quantum number, spin magnetic quantum number, and magnetic orbital quantum number like that. So all these quantum numbers basically it is a part of the topic which is called as vector atom model, because vector atom in vector atom model all these quantities are considered as a vector like the L vector, S vector, and J vector. L vector is orbital angular momentum vector, S vector is spin angular momentum vector, and J is the sum of it. And due to the interaction between orbital angular momentum and spin angular momentum, there is spin orbit coupling, which again gives rise to the fine structure of spectral lines. So we will be solving a few problems based on that. However, before solving the problems, let's talk about some um, let me give you a brief overview of the quantum numbers that we will be discussing in the upcoming time. So, talking about the quantum numbers, initially we have also from past a few weeks we have also discussed about the first quantum number, which is principal quantum number, that is n. And according to the principal quantum number, the cells in which electron revolves around the nucleus is defined, and n has values 1, 2, 3, 4 like that. If n is 1, then that cell is called as K cell, n is 2, L cell, n is 3, M cell, n is 4, N cell. Then another quantum number which came out into picture during Sommerfeld's modification to both theory was orbital quantum number or azimuthal quantum number. So it is azimuthal quantum number, which is small l, and L for uh, n. Suppose principal quantum number is n, then L also has n values. For example, if n is 4, then there corresponding to n equals to 4, there are 4 L values. And what are those values? The L values will be 0, 1, 2, up to n minus 1. So now you can see there are also n values 0, 1, 2. Since 0 is included and it ends with n minus 1, so there are total n values. And corresponding to different L values, we also have different names like L equal to 0. It means S subcell equals to 1, P subcell, then D, then F, like that, corresponding to L equal to 1 and L equal to 2 and L equal to 3. Then talking about the other two quantum numbers, one is orbital magnetic quantum number, another is spin magnetic quantum number. So one is orbital magnetic quantum number, that is ML. Now talking about ML, it corresponds to different states uh, of L. If we have L, then corresponding to that, ML has 2L plus 1 values. Like corresponding to 1N, L had uh, N values. So corresponding to 1L, it has 2L plus 1L values. And what are those values? They are L, L minus 1, sorry. I think there was some L, L minus 1, L minus 2, then 0, minus 1, minus 2, up to minus L. So these are will be 2L plus 1 ml values. For example, if L equals to 2, then ml has 2 into 2 plus 1, that is 5 values. And what are those values? They are 2, 1, 0, minus 1, and minus 2. So total 5 values. Similarly, correct, this quantum number ml, it was related to the orbital moment of the electron. If you talk about the spin moment of electron, then again we have another quantum number, that is S, that is called as spin magnetic quantum number. Spin magnetic quantum number. So it is denoted as ms, and corresponding to the value of S, we have the value of ms. So since it is quite similar to that of L, so corresponding to one S value, we have 2S plus 1 values. And if we talk about electron, for electron S is half, so we have two values of ms, and that are minus half and plus half. So there are these four quantum numbers. So we will solve a few problems that will be based on these concepts. And if you talk about the quantum numbers, you see first in principal quantum number, we principal quantum number was another theory of Bohr or Rutherford. You can say, because Rutherford first suggested that electrons are revolving in certain orbits, and then actually it was named KLMN like that. So first, principal quantum number was explained, and it gave an idea about the energy of the electron in which it is revolving. However, it was found that during the Sommerfeld's modification to Bohr's theory, there was introduction of another quantum number, which is azimuthal quantum number, that gave rise to some correspond to one L, there were more than one levels of L. So there were total n levels of L, whose values was from starting from 0 to n minus 1. And then if you talk about the effect of so if you remember about the drawbacks of Bohr Sommerfeld theory, there are a few drawbacks, like it could not explain the effects of magnetic field on spectral lines, why the spectral lines are being splitted into a number of spectral lines in magnetic field as well as electric field. So all this phenomenon was related to the motion of the electron that gave rise to magnetic field, because whenever an atom is placed in a magnetic field, it will interact only when the atom has an internal dipole moment or internal magnetic moment. So as we continue our discussion, we will find out that each electron which revolves in an orbit has some magnetic moment associated with it. So whether it has orbital motion or spin motion, that will depend upon the nature of the magnetic field. Like if we are talking about the orbital motion, then we have orbital magnetic moment, and corresponding to that orbital magnetic moment, we have orbital quantum number L, and corresponding to L, we have ml. Similarly, if you talk about the spin motion, then corresponding to spin motion, the magnetic dipole moment is spin magnetic moment, and it is related to the quantum number ms. So now we'll start solving a few problems that will be based on those concepts. Now, if you consider about the question one, it says consider an electron in hydrogen atom in its second excited state. What is the magnetic moment produced by it due to revolution around the nucleus? The options are option A, 5.45 into 10 to the power minus 24 ampere meter square. Option B, 7.2 into 10 to the power minus 25 ampere meter square. Option C, 2.8 into 10 to the power minus 23 ampere meter square. And option D, 6.3 into 10 to the power minus 26 ampere meter square. So these are the four options, and the question says consider an electron in hydrogen atom in its second excited state. Then what is the magnetic moment produced by it due to revolution around the nucleus? So these are the four options. So I will give you a few minutes to think about this question and try to solve it. After that, we will discuss how you will approach this problem. Can you all see my screen?
Yes.
Okay, so please solve and then we will discuss. So in last class, I think a few of the students were saying that they are already attending the sessions that are being conducted, I think, on Saturday. So they are finding similar questions here also. So if any one of you want to discuss some other problems, then we can also do that. So if you feel so, then you can tell me, and then we will be discussing some other problems, not the problems that were discussed on the introduction session on Saturday. So can anyone tell me what will be the correct option?
I'm still solving it,
Yes.
sir. 1 minute.
Okay, so please solve.
Sir, is it the third option?
Absolutely correct. The correct answer will be 2.8 into 10 to the power minus 23 ampere meter square. So if we solve it, we know if an electron is revolving, we know according to Bohr's theory, an electron is revolving around the nucleus in certain circular orbits. So an electron, since it has some charge like 1.6 into 10 to the power minus 19 coulomb. So due to this charge, when it is in motion in a circular orbit, then that particular system act as a magnetic dipole, and each dipole we know has a magnetic moment. So the formula to calculate the magnetic moment is mu equals to current into area, because due to the motion of that particle it generates current, and since it is revolving in a circular orbit, suppose this is the orbit and this is r, so the area will be 2 pi, sorry, area will be pi r square. Now if you talk about current, we know the q is equals to I into t, so I will be q by t, and 1 by t is frequency of revolution. 1 by time period is equals to frequency of revolution, so it will be q into frequency. Now if you put it for the motion of electron, that will be e, which is the charge of electron, and then the orbital frequency of electron into pi r square. Now if we talk about the frequency, then what will be the formula for frequency? So frequency f will be velocity by distance. So here the total distance traversed by electron is 2 pi r, that is the circumference of the circle having the radius r. So it is v by 2 pi r. So if you put that, it will be e v by 2 pi r into pi r square, or it is e v r by 2. And if you talk about the unit, if you took SI unit, then it is ampere into meter square. I into A is area. But according to Bohr's theory, we know electron can revolve only in that orbit in which its angular momentum is quantized. And if you talk about the quantization of angular momentum, it is mvr equals to nh by 2 pi. So why we are using this formula here? Because if you see, the informations we have is only related to the motion of the electron in a certain orbit. We have we don't have any information related to the orbitals like L, what is the value of L and all. So here you can see the question is given. The electron in hydrogen atom is in its second excited state. So second excited state means what will be the value of N? Yes.
N will be 3.
Yes, so for ground state, the value of n is 1, first excited state n is 2, and second excited state n is 3. So here, in this case, we will put the value of n equals to 3. Now, if you put the value of n, then we will get mvr is equals to 3h by 2 pi, or vr equals to 3h by 2 pi m. So this is one equation. Now here we had the value of magnetic moment EVR by 2. So if you put the value of VR in that equation, then we will get mu is equals to 3HE by 2 into 2 pi m. Suppose this is 2 and this is 1. Then from 1 and 2, we will get the value of mu is 3HE by 2 pi m. Or you can say 3 He by 4 pi m. So if you put all the values, because we know these values now, what is the value of H?
6.654 into 10 power minus 34.
6.664, let's take, into 10 to the power minus 34, into the value of E is the charge of electron, 1.6 into 10 to the power minus 19, then 4 pi is 3.142 into the value of M. What will be the value of M? We are talking about whose motion?
Electron's motion.
Exactly. So the mass will be mass of electron. It will be 9.1 into 10 to the power minus 31. So all units are in SI system. So if you calculate, it will give you 2.8 into 10 to the power minus 23 ampere meter square. So this will be the correct answer. And if you talk about the units, sorry, if you talk about the options, then the correct option is option C, 2.8 into 10 to the minus 23 ampere into meter square. So is this clear to everyone?
Sir, I have a doubt in this question.
Yes,
In this case, the how can we say that the orbit is circular, sir? Because according to Bohr's Sommerfeld model, the orbits are actually elliptical for few values
exactly. So
of
according to,
K.
so if you see, we can only calculate the frequency of revolution if we know the value of the distance and the velocity. So all these things we are calculating is corresponding to a particular circle. And again, if you see the problem that I was talking in between, we only have the information of N. You see, consider an electron in hydrogen atom, which is in its second excited state. So till now, in this question, we don't have any information regarding the value of N. So since we don't have any information, so we will assume that since we only have the value of N, we only have the value of N, so we will assume that the orbit of the motion of the electron is circular. Then we will solve it. Because if there are, that's why I was telling that, because in this question we know, due to, I was discussing a few times, a few minutes before, that due to orbital motion and spin motion, we have magnetic moments. However, here you see, due to uh, motion in a particular orbit, we also have the magnetic moment. So here we only have the information related to the value of n, because it is in second excited state, the value of n is 3. So we will solve according to that. So we know during the introduction of principal quantum number, it was assumed that the orbit of the electron is circular. So we will use the formula for area is pi r square and the circumference is 2 pi r. Is
Okay,
this
sir.
clear to you? Okay, so we will move to the second question. The question says, Bohr-Sommerfeld theory failed to explain. Option A, intensity variations of spectral lines. Option B, G-Man effect. Option C, Stark effect. And option D, all of the above. So can anyone tell me what will be the correct option? Yes, anyone?
Sir, I'm sure that it failed to explain Zeeman effect and Stark effect, but I'm not sure about the first option.
Okay. So, okay, so you are not sure about intensity variation of spectral lines. Okay, so anyone other? Let me- Yes, I could not hear you at first. Okay, option D, you are saying the last option.
D.
Sorry.
Option D.
Yes, the correct option is option D because the Bohr Sommerfeld theory was not able to explain all the above facts, all the above things like intensity variations of spectral lines, G-man effect, and star effect. Now, if we discuss about why it was not able to explain the intensity variation spectral lines, so the
Mama.
intensity variation, yes,
No, sir. No, sir.
okay, so basically the variation of intensity of spectral lines depends upon the rate of transition. So how the transitions are taking place. So what are the rates of transition? So according to that, we get variations in the intensity of the spectral line. So although the theory was able to explain how the energy levels are arranged or how, like, for example, the electrons are revolving in certain orbits and according to their energy difference, they get the transition occurs. Either the energy is absorbed or the energy is emitted. So it was only in Bohr-Sommerfeld theory, they discussed only about the transitions that was related to the frequency of transition, frequency, wavelength, wave number, like that. But they did not explain anything about the rate of transition. And the rate of transition is related to the intensity because higher will be the rate, higher will be the transition, is not it? So, what do you mean by intensity? Can anyone tell me? If you talk about the light is intense, so what it means in physics?
It is mean by strength, sir. That is concentration.
Exactly. So we have more photons. So more photons means more transitions, isn't it?
Yes,
So
sir.
the rate of transition is related to the intensity of light. So if the rate of transition is maximum, the intensity will be maximum. So since in both Sommerfeld theory there was no talking or no explanations related to the rates. However, they only explained the properties of transition like frequency of transition, wave number, and all that. But there was no discussion regarding the rate of transition. That's why there was no discussion about the intensity variations of spectral line. Now again, if you talk about G-man and Stark effect, there was no discussion about the orbital and spin things. We know the G-man effect comes because of the orbital and spin motion of the electrons because due to the orbital motion. So if we, I think in a few weeks, we will be discussing about the G-man effect in more detail. So there are two types of G-man effect. One is normal G-man effect, another is anomalous G-man effect. So in case of normal G-man effect, it occurs only for singlet states. Singlet state means for the states where the spin is zero. So for no spin, we have normal G-man effect, and for with spin, where the spin is non-zero, we have anomalous Zeeman effect. So in case of normal Zeeman effect, a single line splits into three lines, and in anomalous Zeeman effect, a single line split into a number of more than there are no constant value. It can split into four, five, six, like that. So depends upon the magnetic field. Again, also we have the strength of the magnetic field. Under weak magnetic field, the splitting will be different, and under strong magnetic field, the splitting will be different. So all these things that comes into picture once we start talking about the magnetic moments. And the magnetic moments, there are two magnetic moments. One is due to orbital motion, another due to spin motion. So all these things was not discussed in Bohr's Sommerfeld theory. That's why it was not able to explain the G-man effect and Stark effect also. So all these three things, like the intensity of spectral line was again not explained, the G-man effect and star effect was also not explained. So the correct option will be option D. Because, and if you talk about some other demerits or some other disadvantages of Bohr Sommerfeld theory, so can anyone tell me out of, matlab, I mean, other than these three disadvantages, what are the other disadvantages of Bohr Sommerfeld theory? If you think about the Bohr's theory, Bohr said that, or according to the Bohr, the theory was only valid for single electron atoms or one electron atoms, like hydrogen, helium plus, like that. But it was not, the theory was not made for multi-electron atoms. So again, this was one of the disadvantages, because these things was not encountered in Sommerfeld's theory also, Sommerfeld's modification. Also, if we talk about the distribution of electrons, till now, we have not discussed anything about the distributions, is not it? We are only talking about the transition of, because actually these two things, if you talk about the model for one electron atom, and then the arrangement of electrons. So you see, these two things are interconnected, because since we are only talking about only single electron, so you are not bothered about the arrangement of electrons. So once you start talking about the electrons are more than one, like there are a number of electrons, then we will start discussing about the arrangement of electrons. However, the theory was not able to explain these, again, these another two factors. So because a few things that also a few things that can only be explained in terms of other quantum numbers, like magnetic quantum number, spin magnetic quantum number, orbital magnetic quantum number. So these are a few things that was not explained by Bohr and Sommerfeld's theory. Now we come to question number 3. Question number 3 says, for a system having orbital quantum number L equals to 2, what are the possible values of Z component, that is Lz of angular momentum L? Options are: option A, plus 2h cross and minus 2h cross; option B, plus 2h cross h cross and minus 2h cross; option C, plus 2h cross h cross 0 minus h cross minus 2h cross; and option D, plus 2h cross 0 and minus 2h cross. Yes. So can anyone tell me what will be the correct option?
Sir, is it option C?
Yes. So anyone other? Yes. Do anyone of you have any other answers? So if you remember, during our discussions in the initial part of today's interaction session, we talked about number of quantum numbers, and we talked about the quantum number L, and L correspond to one value of L. We had 2L plus 1 ml values. So that ml value is nothing but it is related to the Z component of that angular momentum, because if you see, during the orbital motion of electron, if we place an atom in a magnetic field, then there are some components of the of that orbital angular momentum along the magnetic field. So that component is called as Lz component. So since, if we talk about the basically these things, since we are talking about quantum numbers, we are talking about quantizations. Like we have some distinct values. We can't take any arbitrary values. Like so, if the name also implies that it is quantum number. Quantum number means the things are quantized. Like if you talk about the value of principal quantum number, the values are 1, 2, 3, 4, like that. We don't have any. non-integer values like 1.1, 1.2 like that. So the energy levels are discretized, like the energy levels are quantized. There are not continuous value of energy. That's why we have different spectral lines. So if you talk about the quantization of angular momentums, basically if you, I think in a few weeks we will be discussing about the quantum mechanical treatment of hydrogen atom. So in that we will be discussing that the units or the units of angular momentum in quantum mechanics is called as taken as h cross, that is h by 2 pi. So that's why we discussed now in board theory to us mvr is equals to n h by 2 pi, that is n h cross. So h cross is the unit of angular momentum in quantum mechanical treatment. So in general what happens, the L, which is the total orbital momentum quantum number, is written as L into L plus 1 root over h cross. And if you talk about the value of Lz, then Lz is given as mlh cross. And we know corresponding to one value of L, we have 2L plus 1 ml values is not it. So since L is 2 in our case, so we have L is 2. So sorry, this is not L. We have small l is 2. Yes, small l is 2. So the capital L will be 2 in L into L plus 1 root h cross. So it will be 2 into 2 plus 1 root over h cross. That is 2 into 3 h cross root 6 h cross. So this is the total angular momentum, total orbital angular momentum. Now, if you talk about the z component, since it is ml h cross, so we have L equals to 2. So what are the value of ml? It is minus 2, minus 1, 0, 1, and 2. So we have 5 ml values. So there are 5 ml values. So correspond to 5 values of ml, we have 5 components of Lz. So this is minus 2h cross, minus h cross, 0, plus 2h cross, plus h cross. So these are 5 values of Lz. Now, if we talk about Lz, we have minus 2h cross, minus h cross, 0, h cross, 2h cross. That is 5 values. So basically, if we will be discussing it in a few minutes, there is another phenomena which is called as space quantization. So like angular momentum values are quantized, the orientation of those angular momentum corresponding to magnetic field is also quantized. The corresponding to a particular orbital angular momentum value like L equal to 2 or L equal to 3, we will be having some discrete orientations with respect to the magnetic field. So here there are 5 orientations. We will be this basically this is called as space quantization. Like the orientations are also quantized. So since orientation is also quantized, the angular momentum can't make any arbitrary angles with the magnetic field. It can be oriented in some particular angles. So there are 5 angles corresponding to 5 values of angles. So if you talk about the correct answer will be again option C, as suggested by someone of you. So it will be option C. I hope this is clear to everyone. Or is there any confusion regarding it?
No, sir. It's clear.
Okay, so we'll move to question number 4. Question number 4 says, so I request you to respond quickly so that we can solve these 10 or 11 problems that is related to the week's lecture. Then if time permits, we'll be solving additional problems also. So let's finish it up quickly. Now question number 4. Question number 4 says, what are the possible values of J for a d electron in one electron atomic system? Options are option A plus 2 and minus 2, option B 2, 1, 0, minus 1, minus 2, option C 1 by 2 and 3 by 2, and option D 3 by 2 and 5 by 2. So these are the 4 options. Now if we talk about the question, it says what are the possible values of J for a d electron in a one electron atomic system. Now, if you talk about the value of J, so again this question related to spin orbit coupling. So if we have L, that is orbital quantum number, we have S, that is spin quantum number, then corresponding to that we have J. Now the values of J, how we will calculate the value of J? So J is L plus S to L minus S with one increment. So it will be calculated like that only. So if we know the value of L and know the value of S, then we can calculate the values of J. So now we need to identify in this particular question what are the values of L and S, and then we will find out the values of J. So I'll give you a few minutes. So please tell what will be the correct option.
Option D.
Any any other answers? Sorry, any other response? Okay, so correct option is option D. Yes. So it is 5 by 2 and 3 by 2. So if you discuss about the values of L and S, so the electron is present in which subcell? It is present in D subcell. So D subcell means what will be the value of L for D subcell? We have discussed earlier today.
L is equal to 3, sir.
L. Are you sure? So L0 is which subcell? S. L1 is P.
L2 is
2 is
D. D.
D. So L is 2 for D. So L is 2, and what will be the value of S? So we know if there is a single electron, here the only information is given to us related to the spin is one electron atomic system. So what is the value of spin for electron? What is the value of S?
Half.
Plus half.
Plus
Yes.
half.
So now, so uh, if you talk about the value of S, so we don't talk about the value of plus and minus because S has value half. Then corresponding to that value of S, we have plus half and minus half as MS. Like in the previous question we discussed, the LZ had 5 values. So corresponding to S equals to half, we have MS minus half and plus half. So we'll be having, if you talk about SZ will be minus S cross by 2 and plus S cross by 2. Is that clear? So since we are not talking about, so here we are not talking about the Z components and all. So if you talk about the value of S, so for electron, S is half. That is, so we all basically say that electron is a fermion, which is a spin half, or electron is a spin half particle. So S is half. Now, if you talk about this line, so what will the value of J? It will be L plus S to L minus S. So what is L plus S? L plus S is 2 plus half, that is 5 by 2. L minus S is 2 minus R, that is 3 by 2. So if you see, we will start from 5 by 2 and then we will start from 5 by 2, then we will add, so we will subtract minus 1, minus 2 like that, and then we will reach at 3 by 2. But if you see, if you subtract 5 by 2 minus 1, it is again 3 by 2, which is also present here. So we have only two values, that is 5 by 2 and 3 by 2. So 5 by 2 belongs to L plus S and it belongs to L minus S. So the plus 1 increment is feasible only when we have some other values of S and L. For example, if you talk about some, so is this clear to you? The correct option will be option D, that is 3 by 2, 5 by 2. Is this clear?
Yes, sir.
So if you talk, I was talking how we will find which one increment and we will be find different values. For example, L is 4, S is 1. So can anyone tell me what will be the values of J? Yes. So what is L plus S?
5.
5. What is L minus S?
3.
3. So 5, 3. There is another value. So 5, then 5, 5 minus 1. So 5 minus 1 is also present here. So it will be 5, 4, and 3. Is this clear? So it will be 3, 4, 5. If we, so corresponding to L equal to 4 and S equal to 1, we have J values 3, 4, 5. Another example we can take, suppose L equals to 4 and S equals to 4. Then what will be the value of J?
It starts from 8 and goes up to 0.
Exactly. So L minus S is 0 and L plus S is 8. So it will be 0, 1, 2, 3, 4, 5, 6, 7, and 8. So it depends upon the values of S and L, that how many number of values of J we can get. So is this clear to you?
Yes, sir.
Okay, so we'll move to the fifth question. The question says, for 2D 5 by 2 state of the electron, calculate the maximum possible value in degree of orientation of vector J with Z axis. Options are option A 32 degree, option B 79.8 degree, option C 147.7 degree, and option D 178.5 degree. So the question says, for 2D 5 by 2 state of the electron, calculate the maximum possible values in degree of orientation of J vector with Z axis. So if you talk about this question, here we have the state 2D 5 by 2. So this 2D 5 by 2, basically this type of notation is called as spectroscopic notation. This is spectroscopic notation. Now if you talk about spectroscopic notation, it is 2s plus 1 Lj. So where L is orbital, L1 means, so here you see the values are, so here we see it is, since it is total quantum number, so the values are capital. So it is, for capital L equal to 1, we have S, L equal to 2, we have P, L equal to L equal to 1, we have P, L equal to 2, we have D, like that. So L is correspond to orbital, S is spin, and J is total. So if you see the question, the spectroscopy notation is given as 2d5 by 2, is not it? So can anyone tell me what are the values of L, J, and S in this case? Yes.
L is 2, J is 5 by 2, and S is 1 by 2.
Yes. So 2s plus 1 is equals to 2. 2s plus 1 is equals to 2. So S is 1 by 2. And since it is D, so L is 2. And also J is written here 5 by 2. So J is 5 by 2. However, corresponding to L equal to 2 and S equal to half, can anyone tell me what are will be the possible values of J? Suppose S equal to half and L equal to 2. What will be the values of J? Will it be only 5 by 2 or will there be any other values? So in the previous question we discussed that corresponding to value of S and L, we have values L plus S to L minus S. So here the values of J will be 2 plus half to 2 minus half. So 2 plus half is 5 by 2, 2 minus half is 3 by 2. So there will be two possible states. However, the question says we need to find out the maximum possible values of orientation of J vector with Z axis. That is J is equal to 5 by 2 level. So if you talk about the orientations, so if you remember we have discussed the corresponding about the orientations. If J is the total angular momentum quantum number, then the orientations corresponding to the Z components is given as JZ. Like in the previous discussions, L and S were obeying. It will be obeying the same principle. Like J is small j into j plus 1 root over h cross, and JZ will be mj cross. So JZ will be the Z component, and corresponding to one value of J, we will be having 2J plus one values of mj. Is this clear?
Yes, sir.
So corresponding to value of J equal to 5 by 2, what are will be the values of mj? Mj will be having 5 by 2 plus 2 into 5 by 2 plus 1. So there will be 6 mj values. So these are minus 5 by 2, minus 3 by 2, minus half, plus 3 by 2, and plus 5 by 2. So there are total 6 values of mj. So corresponding to these 6 values of mj, there will be 6 different orientations. However, we need to find out what will be the maximum orientation, because the question says what will be the maximum possible value or the orientation corresponding to j vector with z axis. So what? So the maximum orientation means the angle between z vector and jz vector. So the formula is given as cos theta, where cos theta is jz by j, or theta is equals to cos inverse jz by j. So if you put the values, jz is mj cross and j is j into j plus 1 root over h cross. So we know if you talk about the cost values, so the maximum of the maximum value of theta will be corresponding to the minimum values of this bracket at all. So the minimum values of bracket at all will depend upon the value of j and mj. Since the value of j is constant, the value of j is 5 by 2 in all cases. So for maximum j, for theta is maximum, what will be the mj value? Mj will be minimum out of the all value, that is minus 5 by 2. So if you put minus 5 by 2 here, what will the value of theta? Theta will be cos inverse mj. Mj is minus 5 by 2 h cross divided by 5 by 2 into 5 by 2 plus 1, that is 7 by 2 root over h cross. So h cross gets cancelled out. We'll be having cos inverse minus 5 by 2 divided by 5 into 7, 35 by 4 root over. So if you calculate it, you will get the value of theta is 147.7 degree. So the correct option is option C. So corresponding to 6 values of mj, we'll be having 6 orientations. So here, according to corresponding to minus 5 by 2, we had the orientation for 147.7 degree. Then there will be theta 2, theta 3, theta 4, like that. So there will be, in total, there will be 6 orientations. So clearly we can say, if we talk about the cos theta values or the theta value corresponding to plus 5 by 2, so corresponding to plus 5 by 2, it will be minimum. So minimum means it will be 180 minus 147.7 degree. So it will give you how much? It will be 32.3. Like that, what will the value of theta at 2? So the value of theta corresponding to minus 3 by 2 is equal to the value of theta corresponding to plus 3 by 2 minus 180, like that. So there will be three values which and corresponding to three values. If you subtract those three values from 180 degree, it will give you the other three values, like that. So I hope this is clear to everyone. Now if we talk about the question number 6. Question number 6 says the maximum angle of orientation of spin angular momentum with external magnetic field for spin S equals to half is, options are option A 54.74 degree, 125.26 degree, and 97.5 degree, and option D 145 degree. So these are the four options. Now the question says the maximum angle of orientation of spin angular momentum with external magnetic field for the spin S equals to half. So here the value of spin is given, S equals to half. So please calculate and tell me what will be the correct option.
Sir, is it option A?
The question says the maximum angle of orientation. Check your answers again. What will be the maximum angle of orientation? So you see, so for a is equal to half, we have two values of ms. So the values of ms are minus half and plus half. So sz is minus h cross by 2 and plus h cross by 2. So s is half into half plus 1 root over h cross. Now, if we talk about theta 1, it will be cos inverse ms by s into s plus 1 root over. So for theta 1, it will be cos inverse minus half divided by half into 3 by 2 root over theta 2 cos inverse plus half divided by 1 by 2 into 3 by 2 root over. So this will be cos inverse. So 1 will be, so in the denominator it is 3 by 4. Root over of 3 by 4 is root 3 by 2. So 2 gets cancelled out from numerator and denominator. It will be cos inverse minus 1 by root 3. It will be cos inverse plus 1 by root 3. So, like in the previous question, we also discussed the maximum value of theta depends upon the maximum value of theta corresponds to the minimum value of m values. Like in the previous question, it was mj, so here it will be ms. So cos inverse minus 1 by root 3, it will give you 125.26 degree. So here in the question we have only two values. So two values means since one value is 125.26 degrees, another value will be 180 minus 125.26 degree. 180 minus 125.26, which will give you 54.74 degree. So these are the two values. So the question says what will be the maximum angle. So maximum angle means maximum angle will be 125.26 degrees. So the correct answer will be 125.26 degrees. That is option B. Is this clear?
Yes, sir.
Yes, sir.
Okay, so the minimum value will be 54.74, maximum will be 125.26 degrees. Again, question number 7, it says, what is the value of Landé G factor for single state? Options are option A 0, option B 1, option C 2, option D 3. So basically this is the Landé G factor is related to a formula that we have for some for each and every state we have a particular value of Landé factor because all states have different value of L, S and J. So there is a formula that involves, so basically there is a formula of Landé factor. That formula is 1 plus J into J plus 1 minus L into L plus 1 plus S into S plus 1 divided by 2 J into J plus 1. Then if we put all these values, we will find out the correct option. So can anyone tell me what will be the correct option for question number 7? The only information we have here is for single state. So if we remember, we discussed about the notations. So this spectroscope notation, this 2s plus 1 is called as multiplicity. Multiplicity. So if 2s plus 1 is 1, it is called as singlet state. If 2s plus 1 is 2, it is called as doublet. If it is 3, it is called as triplet, like that. So here the question says, what will be the value of Landage effector for single state? So for single state means what will be the value of 2s plus 1? It is 1. So corresponding to
1.
2s plus 1, 1. The value of s will be how much?
1/2.
Will it be 1 by 2?
It is 0.
Exactly, it will be 0 by 2. So 0. Because 2s plus 1 is 1. So 2s is 0. That means s is 0. So s is 0. So in this information, we know j is l plus s or l minus s. Is not it? There may be some other values, but basically j, the values of j depends upon j is equal to l plus s and l minus s, then there will be increment of 1. So since here j, so since here s equal to 0, s equal to 0 means j equal to l, is not it? Yes, the total orbital quantum number is j. So j is l plus s. So l plus s, or either it may be l minus s. But here the value of s is 0. So in both cases, the value of j is for a particular state. For a particular state, there are only one j values. So that j values either will be l plus s or l minus s, because it is a single state. So it is quite obvious that for corresponding to a state there is only one j value, so that j value will be l plus s, because since s equal to 0, l plus and the l plus s and l minus s both are same value, that is l. So j will be l. So since j is equal to l, here see, you write the formula again. It will be 1 plus l into l plus 1 minus l into l plus 1 divided by 2 l into l plus 1. Is not it? Because this s term becomes 0 because s equals to 0 and j equal to l. So j equal to l means it will be l into l plus 1 minus l into l plus 1. So l into l plus 1, they get cancelled out. So it will be 0 by 2 into l into l plus 1. It will be 1 plus 0, that is 1. So the value of Landage factor for a singlet state is 1. So the correct option is option B. Is this clear?
Yes, sir.
Yes, sir.
Okay, so we'll move to the next question, question number 8. Question number 8 says the possible spectroscopic terms or term for energy levels of the electron with L equal to 2 for one electron atom is or are. Options are option A 2p3 by 2, option B 2d3 by 2, 2d5 by 2, option C 2p3 by 2, 2p5 by 2, 2d5 by 2, or option D 2p3 by 2, 2p5 by 2, 2d3 by 2, 2d5 by 2. So in the question it says for energy levels of the electron with L equal to 2 for one electron. So in the question it is, the given information is L equal to 2 and for one electron S equal to half. So now you calculate the values of J, then corresponding to J values there will be different levels. And so please calculate it and tell me what are will be the possible values of the spectroscopic terms, or what are will be the possible spectroscopic terms.
Sir, option B, sir.
Yes, once again.
Option B.
Okay, so anyone other? So as we had already discussed, so since we have the value of L and S, the value of J will be L plus S to L minus S with one increment. So since here S is half, so there will be two values because 2S plus 1 is 2 for S equal to half. So 2S plus 1, so the number of values of, so 2S plus 1 is equal to the number of values of J. Since 2S for S equal to half, we have 2S plus 1 is 2. There will be two J values. So that J values are 2 plus half and 2 minus half. So 2 plus half is 5 by 2, 2 minus half is 3 by 2. So for all these so for all these levels, we have j equals to 5 by 2, 3 by 2, l equal to 2, then 2s plus 1 will be 2 into half plus 1 equal to 2. So we have l equal to 2, s equals to half, that gives rise to 2s plus 1 equal to 2, j equal to 5 by 2 and 3 by 2. Then what are will be the spectroscopic terms? So corresponds to L equal to 2, S equals to half, J equals to 3 by 2. It will be 2 because 2S plus 1, 2S plus 1 is 2. So 2, L is 2 means SPD. So 2D, then value of J is 3 by 2. Then for L equal to 2, S equals to half, J equals to 5 by 2. It will be 2D 5 by 2. So these are the possible levels of these are the possible spectroscopic terms, that is 2D 3 by 2 and 2D 5 by 2. So the correct option is option B, 2D 3 by 2 and 2D 5 by 2. Is this clear to you?
Yes, sir.
Okay, so we'll move to the question number 9. In G-man effect, it is observed that the G-man components are separated by 0.12 angstrom for a line of 500 5,000 angstrom passing through a magnetic field. Find the value of the magnetic field. Then question number 10 is the find structure of atomic spectral lines, and then the find the number of possible one the principal quantum number is equal to r. So these two questions we will discuss later because you see the G-man effect will when we will we'll be discussing in more details about the G-man effect and all. We will be solving these questions. Similarly, the question number 10 is the basic question. However, let's solve question number 11, which says find all possible spectroscopic terms for a one electron atom corresponding to the principal quantum number n equals to 3. These are the four options. So now tell me what will be the correct option. So again, since we are all discussing about the questions that are mainly based to spectroscopic terms, so I skipped these two problems, the previous two problems. So we will solve this problem. Then we will solve additional problems that will be again covering those concepts that we have discussed in the class. So I request you to please solve this one, and then we will be discussing some other problems.
Sir, is it option A?
Absolutely correct. So it will be option A. So how did you reach the answer. So can you explain?
Yes, sir. N is given to be 3, so the possible values of L will be 0, 1, and 2. And
Exactly.
because it's given that it's in one electron atom, I took S is equal to half,
Yes.
and corresponding to L equal to 0, it is the S orbital, and L is equal
Yes.
to 1, it is the p orbital, and L is equal to 2, it is d orbital. And since S is
Yes.
equal to half, 2s plus 1 is equal to 2. So the multiplicity in each term will be 2. And corresponding to P, since L is equal to 1, J will be 1 plus half and 1 minus half.
Yes.
And for D, J will be 2 plus half and 2 minus half. And that gives 3 by 2 and 5 by 2 for D orbital.
Okay. So if you see here, like we said, so n equals to 3 means L will be having value 0, 1, 2. So corresponding to L equal to 0 and S equal to 0, we have J equals to 0, is not it? Sorry, here S is not equal to 0, it is a 1 electron atom. So 1 electron atom means S is half. So corresponding to L equal to 0 and S equals to, so corresponding to L equal to 0, S equal to half, we have J values half. Corresponding to L equals to 1, S equals to half, we have J values 3 by 2 and half. Corresponding to L equal to 2 and S equal to half, we have J values 5 by 2 and 3 by 2. So correspond these terms since S is equals to half, so 2S plus 1 will be 2. So here the value of the spectroscopy term will be 2S half. Then here it will be 2P half and 2P 3 by 2 because here L equal to 1. L equal to 1 means it's P, L equal to 0 means it's S. And then for L equal to 2, it is D. So 1 will be 2D 3 by 2, 2D 5 by 2. So these are the 5 cells. So the possible spectroscopic terms corresponding to the quantum number n equal to 1 and 1 electron is 2s half, 2p half, 2p 3 by 2, 2d 3 by 2, 2d 5 by 2. I hope this is clear to everyone. Now we will solve a few problems, some other problems. Let me add a few slides. Okay, so the question says a thin uniform ring carrying charge q and mass m rotates about its axis. What will be the gyromagnetic ratio of the ring? So there is a uniform ring carrying charge Q, mass M, rotates about its axis, rotates about its axis. So what will be the gyromagnetic ratio of that ring? What will be the gyromagnetic ratio of that ring? So can anyone tell me what do we exactly mean by gyromagnetic ratio?
It is the ratio of the magnetic dipole moment to the orbital angular momentum.
Exactly. So it is the ratio of the dipole moment to orbital angular momentum. So it is mu L by L, or the magnitude of L vector. So please calculate and tell me what will be the value of gyromagnetic ratio.
So here is the axis of rotation along the diameter of the ring.
Yes, it rotates about its axis. Axis means the central one that is passing through its center. For example, this is the ring, this is the axis. It is rotating like this about the axis. It has mass M and charge Q. Yes, what will be the gyromagnetic ratio? So if we solve it, we will follow the same approach that we discussed in the first question of today's session. So the magnetic moment mu is charge into area. Sorry, current into area, I into A. So current is charged into frequency, and frequency is the velocity of revolution and the circumference. So it will be Q divided by 2 pi r into V into area is pi r square. So R1 R gets cancelled out and pi also gets cancelled out. It is Q V R by 2. However, if you talk about Bohr's postulate, L we know it is mvr equals to nh by 2 pi, or if you want to put, we can put L equals to mvr. So Vr is L by m. So mu is equals to q m vr by 2m. So MVR is angular momentum. This MVR, it is L. So mu is QL by 2m, or mu by L is Q by 2m. Is this clear? The gyromagnetic ratio will be Q by 2m. Is this clear to everyone?
Sir, can you show the previous slide once, sir?
Okay. Yes. So this is the previous slide. Don't confuse with the unknowns. The question is pretty much similar to the previous question, but in the previous question we had the values of n, h, and 2 pi. We had the values of n, so we put that value. But since here we don't need to put the value of nh by 2 pi because we need to find out the ratio of mu l and l. So in place of l, we simply put mvr. So if you put the value of l equals to mvr, you will get vr equal to l by m. Then from L by M, we will get mu by L is Q by 2M. I hope this is clear to everyone. Yes.
Yes, sir. Yes, sir.
Okay, so we will solve another one. So, can anyone tell me what are the basic quantity or basic unit associated with the magnetic dipole moment? The atomic magnetic dipole moment. Or what is the unit? Basically, the expression or the dipole moments are expressed in terms of what values. Like what basically, if you say what is the unit of atomic magnetic dipole moment? Do you know about Bohr magneton?
Yes, sir.
So Bohr magneton, basically, this Bohr magneton is nothing but mu b is Eh cross by 2m or Eh by 4 pi m. So this, so basically all the uh, dipole moments or atomic dipole moments are expressed in terms of Bohr magneton basically. So Bohr magneton, the value if you calculate, it will be coming out some 9 point something like that. So this is the unit of basically all. For example, if we talk about the wavelengths, generally the wavelengths are expressed in terms of nanometer or angstrom. Like that, if you talk about the dipole moments in case of atom, the the unknown, the known unit or known constant is Bohr magneton. And if you similarly, if you talk about the dipole moment of nucleus, then it is nuclear magneton, which is Eh cross by 2mp, that is mass of proton. So, which will be higher? Whether mu b will be higher or mu n will be higher? Yes,
Mu B will be higher.
exactly. So mu b will be higher because the value of me. So here m is electron mass of the electron. Since mass of electron is very small as compared to mass of proton, so Bohr magneton, the value of Bohr magneton will be higher than nuclear magneton. So let's solve another question related to this concept. So question says calculate the possible angles between L vector and S vector for a d electron in one electron atom. So calculate possible angle between L vector and S vector for a d electron in one electron atom. So can anyone calculate? So basically, there is a formula like we calculated the expression for the angle between LZ and L, JZ and J. So there is a formula using which we can calculate the angle between L vector and S vector. So if you derive the formula, basically it starts from J vector is L vector plus S vector. So J square will be J vector dot J vector, which is L plus S dot L vector plus S vector. It will be L square plus S square plus 2 L vector dot S vector. So J square minus L square minus S square equals to 2 L vector dot S vector. So this is nothing but 2 LS cos L vector and S vector. So we need to find out this value. That is the angle between L and S. So this is, so the cos of L vector and S vector is J square minus L square minus S square divided by 2 LS. So we know J is J into J plus 1 root over x cross. So J square will be J into J plus 1 x cross square. S square will be S into S plus 1 x cross square. L square will be L into L plus 1 x cross square. So what will be the value of angle between L vector S vector? It will be J into J plus 1 J square minus L square L into L plus 1 minus S into S plus 1 divided by 2 L into L plus 1 root over S into S plus 1 root over. So if you put the values for d electron in one electron atom. So for one electron atom, S is half, one electron atom, S is half, D means L equals to 2, SPD. So corresponding to L equal to 2 and S equal to half, we have, sorry, corresponding to L equal to 2 and S equal to half, we have J equals to 2 plus half, 2 minus half. So 5 by 2, 3 by 2. So for one case, we will put j equal to 5 by 2. And for another case, we will put j equal to 3 by 2. And we will calculate the values of the angle between L vector and S vector. So please calculate, put the values here and calculate and tell me what will be the values. So if you put the values corresponding to 5 by 2 and 3 by 2, so corresponding to 5 by 2, it will be 61.9 degree, and corresponding to 3 by 2, it will be 135 degrees. So here you see in the angle between LZ and L, we are we basically we saw if one value is theta 1, another will be 180 minus theta 1. But here it is not the case because here we are calculating the angle between L vector and S vector. So these two are quite different. Since in the previous case we are only calculating the component of Z vector of some same vectors, the component of Z a Z component. So it was L, LZ, S, SZ like that. But here it is L and S. So the relation 180 minus theta that does not hold here. So these will be the two angles, possible angles between L vector and S vector. So with this we come to the end of today's interaction session. So is there any doubt?
No, sir.
Okay, so with this, we will end today's interaction session. In the next session, we will be discussing a few problems that will be mainly based on week 5. I think that covers the concept of spin orbit coupling and all that things. So in the next session, we will be discussing all those things. So once again, I thank you all for joining today's interaction session. So if you have any queries or any doubts, you can also ask me now.
Sir, even though, hello,
Yes?
even though you clarify everything, suppose if we get another questions, mean we are struggling a little bit. So I think we have to go through the portions once again.
Yes, so all these things, if you try to solve different questions, so this is one. So mainly the concepts under these questions are similar, but with practice, it will get better and better. So as you start solving few more questions, then you will be able to solve the questions. So you can look for questions in internet and other things like books also. Then start solving those questions. Then you can also solve the questions that you will be facing in the exam. Basically, it is a part of the preparation for the exam.
Okay, sir.
Okay, so good night all. That's it for my side.
Thank you. Okay, sir.
Okay,
Good night,
welcome.
sir.
Good night.